Okay, the final thing we're going to look at today is where this formula comes from, because it's so nice and useful. So the format that is easiest for us to prove it in is actually this the one that we use to take inverse Laplace transforms. Okay, so if we take a look at what this is saying, so if you imagine having your function like f of t, we're going to be looking at the Laplace transform of ua of t f of t minus a. So the ua of t piece means that we're equal to 0 until we get to time a, and then we're equal to 1. So it's going to like turn on our function. That f of t minus a piece is going to take our f of t function and it's going to shift it to the right by a. So basically what it's going to do is say, we're going to take what this value was here at 0 and we're going to shift it so that it starts here at a. Okay. And so what we're going to do is just take a look at our integral. This is going to be a nice, easy fact to do from our integral. So this is f of t minus a, but by being like multiplied by this ua of t function, it just is going to be equal to 0 up until sort of where we would have at that like starting point at 0 in the original function. Okay. So we are going to like push our function over by a and then 0 everything out until time a when we get started. And to prove this, we're just going to use the definition. So the Laplace transform of ua of t times f of t minus a is going to be equal to the integral from 0 to infinity of ua of t f of t minus a times an exponential e to the negative t times s dt. Now looking at our graph, we see that our integrand is actually like equal to 0 up until time a. So we don't really need to do anything from 0 to a. Our integral is just equal to 0. Okay, so this is equal to just the integral from a to infinity of f of t minus a times e to the negative ts dt. So remember that ua of t is going to be equal to 1 when t is bigger than a rather, and it's going to be equal to 0 when it's less than it, which is why I'm not writing it in this expression at all. Okay. So to rewrite this in terms of a, we're just in terms of the Laplace transform of f of t, which we're interested in, we are just going to do like a little u substitution. Okay, so we're going to let u be equal to t minus a. Our upper bound is still infinity. Our lower bound is going to be a minus a, or 0. And everywhere we see a t, we're going to write t is equal to u plus a. All right, so let's plug this in. Our bounds are 0 to infinity, f of t, e to the negative, okay, where we see t, this is equal to u, or, this is supposed to be f of u, e to the negative u plus a times s du. All right. Now, this exponential term, we can distribute if we like, 0 to infinity, f of u, e to the negative us. And then we have a factor e to the negative as du. It doesn't have any t's, or it doesn't have any u's in it, rather. And so we can just bring it out in front of our integral. We get e to the negative as times this integral from 0 to infinity, f of u e to the negative as ds. Well, that is the Laplace transform of f. So this is e to the negative as times the Laplace transform of f. Yay! So that wasn't too bad. Just a little bit of integration to do. Just the use of it. But it's super useful. And then to get the backwards direction, basically we change our name of our variable from t to where we define like tau equals t minus a. And so then our formula looks like f of tau. And then this becomes f of tau plus a. Okay. And so that gives us our other version. All right. And that's it for today. Good work.